Okay, so after watching the video, I was thinking about this question.
Yes.
From the video, I gathered that X-ray crystallography is used to determine the 3D molecular structure of big molecules like proteins.
Right.
Okay, so my question is, there are other methods that you can also use to make molecular structure determination, other instrumental methods.
Other methods.
Okay.
Yes, there definitely are.
Why not those other methods? What's so unique? Why would you use X-ray crystallography over NMR? Other methods.
Yeah, absolutely. So yeah, that's a great question. So NMR is actually widely used for some proteins as well. The real limitation with NMR is when you get to a large protein, anything maybe bigger than 15 kilodaltons or so, it gets very difficult to actually read all the different peaks. Do we all here have experience looking at NMR spectra?
No,
No,
you might want to come down.
right. Most of us don't know anything about NMR or yeah. So,
Or IR.
well, IR, infrared.
Yeah.
Sure. No, well, so NMR is very useful for small things. NMR, you get kind of like a series of spectra, like peaks, if you will, that correspond to every NMR active atom that's in your sample, right? But when it comes to a really big protein, you get a very there's a limitation with the number of peaks that can be deconvoluted because you have to use software sort of do that. So yes, NMR is actually very useful for smaller proteins. So I was actually just at Argonne National Lab out in Chicago just this past Saturday, and the beamline there is basically able to diffract crystals of just about any molecule. That's really the nice thing about X-ray crystallography. You can, as long as you can crystallize it, and now see, I must say that's really a limitation of X-ray crystallography as well. If you can't crystallize it, if you can't get crystals, then obviously it's a no-go. But for some of those bigger molecules, that's really the only way, the only good way at least to take a look at the structure. So we try very hard in this lab. We spend a lot of time trying to find just the right way to crystallize our proteins. So now if you have something even bigger, if you have something maybe above 200 kilodaltons or so 20 times the limit of NMR, then you can use a third technique, which is cryo-electron microscopy. Has anyone here heard of cryo-electron microscopy? So it actually is the method that actually won a Nobel Prize last year in chemistry. There were 3 scientists who determined, who sort of discovered the method and how to sort of use it towards structure determination of macromolecules. How that works is it turns out that if you have something big enough where you can use an electron microscope to visualize it, you can use software to make it a class average, because of course molecules are always moving in solution. So if you freeze the solution in a very precise manner, freeze all your molecules, and get a good look at them through an electron microscope, you can actually solve structure that way by making it an average of all the different orientations, combining them together into one model. But again, that's a technique that's sort of still being developed, and we're still kind of yet to see the full potential of that. But till then, X-ray crystallography, I think right now is, at least for the proteins we work with in my lab, is really the best way to get a sense of the structure. I hope that answered your question. I gave a pretty long response, so if I ever lose you guys, please let me know. I'll reel it back in.
Do you get this question? I wonder, do you work with Diamond? Does your lab collaborate with Diamond?
Yeah, so great question. So Diamond, we actually don't quite go to Diamond since we're at Purdue. We're very lucky because we're actually only about a 2.5-hour drive away from the advanced photon source at Argonne National Lab. It's just as good as diamond. It's actually, I think, a little bit older, but the beamlines are constantly being upgraded. And but it's much the same. It's an accelerator ring that that's able to produce extremely high intensity X-rays for people to use for determination. I'd love to. Would you guys like to get a sense of how it works in terms of going there and shooting your crystals?
Sure.
Yeah. So the first thing you got to do is you have to apply for beam time. So there's a limited number of lines available for protein crystallographers. Most of the beam lines are kind of used for other things. Material science is a big use. Also particle physics, high energy experiments there. But there's I believe 6 or 7 beam lines that are available for general use. It's publicly funded, so it's free actually. There's no cost really associated besides, of course, transportation. And what you do is you basically have to apply online. You have to write up a little proposal, say, hey, look, I have a lot of protein crystals. I'd love to diffract them someday. And then they'll give you a date for you to go to Argonne. Now, you can either mail your packages, ship them out, and you can do this for diamond as well. In fact, sometimes when Argonne is down, or if it's very busy for a few months and we're dying to do some crystallography experiments, we do sometimes contact other beam lines, such as Diamond or Berkeley out in California or Stanford like sorts as well. But typically when we go to Argonne, they'll give us a time, and we're of course fortunate to be located within driving distance. So we actually usually just go there ourselves. And what happens is every beam line has its own team of experts who are kind of in charge of taking care of all the equipment and everything. Like, they're the beamline staff. So every time we make a trip, we're assigned a member of the staff to kind of help us and guide us with any questions that we might have with the software or any of the equipment. We then take our crystals, we'll mount them on the beamline. The beamline will have, so now one important thing with the crystals is X-rays are very they're really intense. They're very high energy, and there's a huge risk, right, of damaging your protein. It's not going to be of any use if your crystal's just destroyed, right? But what we have to do is, the way we deal with that is we keep everything very cold as possible. So on the beamline, there's also a cryojet that just kind of shoots liquid nitrogen at your crystal at a constant rate, so that everything is kept cold. And then we have to close what we call the hutch, which is the whole little room, the space where the beamline is. We close it off, we seal it with a door so none of the X-rays can come out and cause any danger. And then there's a computer display where we then play with the X-rays. So we basically can, the beams are very small, so they're actually smaller than our crystal. So we can actually choose what spot on the crystal we want to hit with X-rays. And then our detector is also there that we can see, and we can observe diffraction spots. I think in the video you guys saw pictures of diffraction spots. Is that right? So if your crystal is good, you'll see a really nice pattern of diffraction spots. If it's not so good, the spots, you may see only a few, or if it's really bad, you might not see any at all. So that's really the challenge with crystallography. How do you make sure that you get those spots? And a lot of that happens to be tied up in how good your crystal is, how well packed it is. The crystal is, of course, a repeating pattern of molecules, right? If they're not well packed, there's defects. Your diffraction, they're not going to diffract X-rays quite as well. It's simple as that. So that's sort of how we do it there.
How do you do your packaging? You know that your results repeating patterns, like you just said, in the crystals.
How do you grow crystals? Like, make sure that you have a good crystal to look at.
That's a very good question. So of course. It's not always correlated with how good it looks, but it's fairly correlated. So what we do is we take our. Let me give you. I can give you guys an example. So I'm in my crystal room. You see behind me, there's some cupboards which are full of what we call crystal trays. So I'm going to take one out for you guys. Okay, so to grow good crystals, you of course need a really good protein sample. Now, you generate your protein sample. Let's assume that we've made ourselves some good protein. You take that protein and then you use a micropipette to basically pipette it into what we call a crystal tray. A crystal tray is going to contain, right along the bottom here, you guys can see, as you can see, there's 96 wells, little wells in each tray. Each well is going to contain what we call a crystallization. So that's usually, it consists of some sort of precipitant and some sort of salt. These precipitants are basically the way they're made is that they're chemicals which are known to cause proteins to start sort of coming together. And the hope is that the idea is that those would induce crystallization. Now, obviously, not all things are going to work for proteins. That's why we have to use several different ones. We have to try them out to see which ones work. It's sort of like a trial and error sort of method. But what you do is now, can everybody see that there's really small wells next to the big wells?
Yeah.
These really small wells are where we put our protein, a little drop of protein. And then what happens is, and then we take some of the reservoir and add it to our protein. What then happens is that the reservoir will induce crystallization with this. There's 96 conditions that we can look at, and we look at those through in the we'll spend a lot of time on the drop and seeing if there's any crystals. Now, if there are crystals, chances are we can improve them. And the way we improve them, there's several methods we can do. What we first try to do is grow them in a bigger drop with more protein. Typically, when you have more protein, there's a good chance you'll get crystals that'll pack much better since you have more molecules. Another thing we can do is we can change those conditions just a little, very slightly. For example, I had crystals that I diffracted last Saturday, which were in a solution of 25% polyethylene glycol with 0.2 molar sodium malonate. That's just a salt. And that was at pH 7. It turned out that when I changed the pH to pH 9, the crystals got much bigger and much nicer looking. It turned out those nicer looking crystals did diffract better. It's not always the case that nicer looking crystals diffract better, but it's a good bet. So I was luckily able to do that. And so the crystals that were right from the tray turned out not to be the best in terms of diffraction, but we got a lot more spots when we changed the condition that the crystals grew in just slightly.
I heard the word synchrotron. Can you explain what is the synchrotron? Is that like X-ray or the name of the machine?
Yeah, so a synchrotron basically is a source of X-rays. So there's a couple ways we can generate X-rays, right? The easiest way is, a generic sort of medical X-ray device. Unfortunately, those X-rays are not, it turns out, powerful enough to really diffract crystals, protein crystals especially, in a meaningful way. The reason is that the more intense the X-rays, the more intense our spots on the detector will be. Now, there are X-ray sources before synchrotrons that consisted of a electrical source that was rotating, generating electromagnetic radiation. It turns out if you take a copper anode, rotate that quickly enough, you will get a fairly strong X-ray beam that is able to diffract protein crystals. However, a synchrotron is the best. So what synchrotrons do, they accelerate electrons very quickly around a ring. And how do the electrons move around a ring, you may ask? It turns out that if you use these very powerful electromagnets to bend the electrons, as the electrons bend, they give off significant amounts of electromagnetic radiation, a lot of which is X-rays. Now, you can capture those X-rays and channel them through a beam, and those beams are basically your beam lines where we can mount our crystal and see what happens there. So synchrotrons are actually the most powerful way to produce high-quality X-rays. And to give you guys a little bit of perspective, when I was using my home source, which is at Purdue University, we have our own X-ray source. It's not a synchrotron, however, it's just one of those old-fashioned sources I was telling you about earlier. If I want to get diffraction of my protein crystal there, I need to expose that crystal to that X-ray beam for 15 minutes. On the other hand, when I'm at a synchrotron, I can expose that same crystal for about just 4 seconds, and I can get a similar diffraction pattern. So there's a lot more you can do with a synchrotron in that way.
Is there any like health standards over time you were wearing like these rings to check how much radiation researchers have been exposed to? It sounds like to be quite safe today. Do you still check some devices that you wear to make sure?
Yes, good question. So it turns out that our X-rays, yes, there is a risk associated with that, but it turns out we can just, the way these hutches are set up, there's a lot of safety measures. For example, there's 2 shutters that are able to block the X-ray beam. And then there's a whole hutch door that we have to first close before the shutters are even allowed to open. So those are the safety measures that we use to avoid any exposure to X-rays. Yeah, the beamline staff, when they're actually fixing the shutters and stuff, yes, they have to be a lot more careful with their Geiger counters and wearing the radiation dose detectors. But luckily, we're in pretty good shape with the safety measures that are in the beamline. Yeah.
So, this question is the benefit from our students that are here. They're here majorly, I would think, to learn something from you, a real scientist. So it's not meant to rigor you or to poke you, or it's not meant to be any negative question.
It's not a dissertation defense.
No.
So, why did you sign up to be a Skype scientist?
Yeah, that's a great question. So I love science. The way I sort of got into this whole thing was by doing research as an undergraduate at Valparaiso University. It's a very small school, and they didn't really have a huge research program. But after visiting Purdue and kind of seeing the facilities that they have, it was very eye-opening, and I think especially talking to my advisor currently, and the way graduate school, of course, works is you choose a professor to work for, work in their lab, and you're sort of their graduate student. And basically, my advisor now, Professor Das, he told me a lot about crystallography, something that's not really taught in undergraduate institutions. It's not, and I think it's a concept that everyone can sort of, I think, appreciate, because I think everyone can see how it's important to be able to look at the structure of molecules. I think it's the easiest way to study them, right? The real problem with molecules, they're just really small. It's hard to really get a naked eye sort of look, and I think X-ray crystallography is the best way to do that. But I really want to bring that appreciation to people in an undergraduate or other setting, to hopefully inspire more people to maybe possibly go into that, or at least have an idea of how it works, because I think it's really important. If you think of all a lot of drugs that are medicines that are invented over the past 10, 20 years, a lot of them use X-ray crystallography, because what are drugs, what are medicines? They're molecules that are able to bind to proteins, right, for the most part. And by solving a crystal structure of your protein bound to the drug, you can identify ways to improve upon it. You can identify ways to maybe make it stronger in its binding. And a lot of that sort of process is an integral part of drug discovery these days. You know, there were 2 beamlines at Argonne National Lab that are solely dedicated for pharmaceutical companies to come and send their crystals to optimize their medicines and drugs.
Can you explain your research? What kind of proteins you are trying to visualize and why? What's the importance?
Yes, absolutely. My protein is called MAVC, and just to give you a very quick overview of how it works, it's a protein that is it's not a human protein, it's a bacterial protein. So it's actually expressed by a bacteria called Legionella pneumophila. So if you've heard of Legionnaire's disease or Legionella, every now and then there's an outbreak of that in the U.S. It's pretty dangerous, you know. I believe the case fatality rate is something like 20 to 30%. So not something you want to have. It usually comes from the water supply. But what's really interesting about this bacteria is it's what's known as an intracellular bacterium. A lot of times, bacterial infections, bacteria just sort of live in your bloodstream. They'll just grow and divide, and they secrete toxins, and that's what makes you sick. Legionella, on the other hand, actually invades into your cells, your macrophages in your lungs specifically. And when it's in your cell, it can cause a lot of problems, and that's where it sort of continues its life cycle within your cells. Now, how do you stop that? And how do you even study that? We have collaborators in the biology department here who are really good at culturing Legionella and finding out what it actually does. And they were able to find that Legionella, when it invades a human cell, it releases several of its own proteins into your cell. And these proteins are actually specifically designed to hijack your cell's own processes for the benefit of the bacteria. So I believe of all bacteria that are known, Legionella has the highest number of these proteins. These proteins are called effectors because they have an effect on the host cell. Legionella, I believe, has over 300 effectors that have been identified. So you can imagine a big challenge to be able to study all of those. Now, the one that I'm really interested in is called MAVC, which is able to hijack your host cells' signaling processes, specifically what's called ubiquitin signaling. Ubiquitin signaling is how your cell is able to recycle its own proteins. It's one way that your cell can destroy foreign proteins. So you can imagine that it would be desirable for the bacteria to be able to either shut down or slow down or change host ubiquitin signaling so that it doesn't target the bacteria itself. If you were a bacteria, you wouldn't want that to happen. So of course, it makes sense for you to send out things that can potentially block that. But the problem is we don't know much about MAVC. So my approach to sort of trying to study it is through some biochemical techniques, which I do in the wet lab, but with a focus, however, on X-ray crystallography, so that I can get the structure, and so I can understand the function much better of this protein. So one thing I'm also doing is trying to solve the structure of MAVC in complex with some small molecules that I think may all down the line serve as drugs or medicines for it.
So how far have you gone with this research? How close are you to relating your results to a drug that can be used in whatever pathway of the Legionnaire infectious?
I guess what we want to do is that, how many times do you have to try before you actually get one result that's useful, that you feel like can help you answer the question. I know that most people think that sounds sort of cool because they just do this one experiment and they got the result. But can you share some of your story?
Yeah, no, absolutely. So that's really a big challenge. Finding the right molecule, finding the right crystallography condition, right? But I think one nice thing about me being a chemist is sort of working in such a collaborative environment. So I work with people. I don't really just work in this lab. a lot of stereotypes of scientists that we kind of just stay in our own lab, work on our own thing, and that's it. Instead, what I would say my experience here has been very different. I meet just about every week with people in our biology department who know a lot about Legionnaire's disease and Legionella in the life cycle and stuff like that, which I don't really know and I don't really study as much. And I also collaborate with medicinal chemists who are really good at designing molecules, who are really good at optimizing molecules. They're really good at the organic synthesis of those things. So I sort of serve as the interface where I can, as a biochemist, I can sort of gain information from the biologists, try and apply that to my system. For example, if I know that MAVC interferes with ubiquitin signaling, I can try and see, one thing I'm trying to do is crystallize MAVC in complex with ubiquitin by itself to see how it interacts with ubiquitin. Small molecule that's, of course, important in ubiquitin signaling. If we can potentially block that interface with some sort of molecule, that would be very useful. And thus far, you know, what I try to do is I try to get some ideas. For example, in terms of the context of drugs, I try to get a list of inhibitors that I can then send out to the medicinal chemists, who will then try and optimize them better and make them better. So yes, a lot of times they don't work out, unfortunately. I'm really lucky, I think, to be working with a lot of people that can be of a lot of help in that regard. So one thing I think you'll learn as a scientist is you can't just rely on yourself. You have to learn how to work with other people if you want to you know, be successful, I think.
How do you go about isolating a specific protein that you're looking for?
I'm sorry, can you repeat that?
How do you go about isolating the specific protein you're looking for?
Oh, that's a great question. So yeah, so we actually don't isolate it from Legionella. You might think it's a Legionella protein. Why don't you just grow some Legionella? You can do that, but also Legionella is very hard to grow in the lab. It's also, of course, dangerous. So an easier way to do it and a safer way to do it is actually through recombinant protein purification. Has anyone heard of recombinant protein in DNA?
We will learn. Not yet, I guess.
Sure, sure. So quite simply, we know that, of course, protein comes from DNA. We take some DNA of the protein you want. You'll put that in actually E. coli bacteria. It's a very simple model bacteria that we can use to actually grow protein. So it turns out if you take some DNA that you want and what we call transform, you transform it into bacterial cells, E. coli cells. E. coli grow like crazy. They're really easy to grow, and they're able to produce protein like crazy too. So we can actually get them to produce whatever protein's in that DNA. We can induce them to produce a lot of it. And then what we do is we break open the E. coli cells using, you can use a variety of techniques for that, but what we do is we just press those cells really hard to sort of squish them and send and release their proteins. From there, now to isolate that protein among all the other proteins that are in that mixture is, I think, the root of your question. And excuse me, the way we really do that is, I think, pretty interesting. So it turns out all proteins have their own charge. They consist of strings of amino acids, right? And each amino acid, there's a variety of amino acids that have their own charge. And it turns out the protein that we're looking at has a very distinct charge. It's it turns out it has a very negative charge. So what we can do is we can use a specific method called ion exchange chromatography to separate every protein there out based on charge. And the way that works is we have you take what's called a column, and the column consists of it's almost like a tube that's filled with large molecules, large beads, if you will, that all have a certain charge, have a positive charge in this case. Now, send your cell lysate, which is your cells that are burst open the protein mixture. You send that through the column. The protein of interest, which we know is very negatively charged, it's going to stick to the positively charged column. It's not going to flow through there, but everything else will flow right through the column. So that's really the main way that we can isolate our protein. There's other ways, but this is how we sort of do it in this lab. I did at least with this protein. And then what we do is, of course, we send a high amount of salt through the column to really wash off anything that's still stuck to the bead. From there, a way to finally sort of, we call it the polishing step, where we just remove, we really try to just isolate that protein, because it turns out there's always a couple other highly negatively charged proteins that also stick to the column that we don't want. The way we remove them in the end is what we call size exclusion chromatography, where we take a tube which is able to separate things out based on size instead of charge. And by doing that, we can then get a pure solution of just the protein that we want. Another way that people do it is called affinity chromatography, where you can put what's called a tag of certain amino acid residues on your protein, and then have some sort of tag. And if you have something that can specifically recognize only that tag, then you can also isolate your protein of interest that way with some sort of chemical or amino acid based tag.
That's right. In your study, one of the most complex molecules you had to basically look at or work with.
Can you say that one more time? Sorry.
In your studies, what do you think is the most complex protein molecule you've had to work with?
Is one more difficult to work with than the other?
Yes, definitely. I think so. A couple of years ago, when I was actually first starting out, we were trying to. So to give you guys a perspective, proteins are typically 200 to 500 amino acids in general that we work with for at least X-ray crystallography. The protein I worked with just past Saturday, NAFC, was 462 amino acid residues in size, which is a size of, I think it was about like 40 kilodaltons. One of the first proteins I worked with when I was kind of a first year, we were all really excited about it. We had a guy who just graduated and wrote his thesis about it, but he hadn't gotten the structure yet. It was called SDEA. It's another Legionella effector, actually. That protein turned out to, so it had 1,500 residues. So it was almost 4 times the size, 5 times the size of what I'm working with now. What was really cool about it, though, was that you might think it's just one large blob of amino acids the way the protein looked. It turned out to be very modular. It had one part that was able to perform one function. It had a second part that was almost folded in its own way that was able to do a second function, and a third part whose function is actually still unknown, that people are still sort of investigating. So that was actually a really cool, complex story. It was almost like working with a system of different proteins, but it was all in one. So every so often you get things like that where you have like a really complex protein in that way.
Are you a first college student? I think I was mentioned by the organizer from the
Yes.
Yes. Can you share with us your experience, like from growing up, like whether you like science or like how you decided finally to become a biochemist?
Can you say the first part of what you were saying again? I don't know if I completely caught it.
I want to share. Well, if you could share with us like your path of growth, to where you are right now, starting from like when you were maybe elementary school. Like, was
Sure.
one, for example, a teacher that inspired you, or what was that one thing that made a big change?
Yes, absolutely. So I actually went to college. I went to Valparaiso University, not really knowing what I wanted to do. When I was in, I think before that, when I was in high school and middle and elementary school, I was really, I liked science. I actually liked biology a lot more than chemistry at the very beginning. I loved living things. I liked studying about things like that. When I was in high school, I took it was an advanced biology class my senior year, and that class had a biochemistry section. I'd taken chemistry the year before, but it was actually I appreciated it, but it wasn't really something I fell in love with right away. But when I took biochemistry, where I sort of they related the function of life to chemistry, things like bonds and atoms and molecules, right? I really appreciated that. I really liked it. And I think it helped me actually understand biology and chemistry a lot better, getting a sense of the interface between those two fields. And yeah, I think because of that, I was inspired to go into college to study biochemistry. I had no idea at the time what I wanted to do with that, which of course was a big risk. But I think especially after my first year, I really got a chance to at least help out in the research lab. I love the environment, and I like seeing people get excited about discovering new things. So the other nice thing that really I think was the final nail in the coffin of me going to grad school was, if you will, was that kind of realizing that grad school, it's not for PhD programs at least, you actually get paid. There's no tuition. That was pretty awesome. So that really kind of sealed the deal for me. So because of that, I really applied to quite a few programs, and I loved Purdue. So here I am now. I think that was definitely important. You always have to take finances into consideration, right? But that really was nice, and I think that's a really nice thing that if you go to a lab, if you make sure it's well funded. One thing I really enjoy doing here is writing grants, and my boss really helps me work on that because he involves me in writing the grants. He's like, you're the guy who actually does the work, who actually is right there doing, the lab work every day. I need your help in writing grants. So, and it's a lot more motivating when that grant means that you're the one getting paid from it, right? So, so yeah, that's the other nice thing about grad school. There is plenty of grant money out there. There's a lot of fellowships you can also apply to. There's quite a few people in my section who were able to successfully get fellowships, which means you don't have to teach. So typically the way it works is you have to serve as a TA to earn your graduate stipend, right? But if you're either on a grant or a fellowship or something like that, you can spend all your time as a researcher. So yeah, that's really sort of the path that I took. I always liked biochemistry, but then that there was a viable path to like a PhD or to a higher understanding of it, really was great. And I think that's something that should be everyone should keep in mind. I think if they're interested in learning more and choosing a career in that field.
And what was done when you what is the process of that? Is it on a medium itself, or is it being like real time or something like that?
Can you say that one more time?
Capturing the X-ray diffraction, is it being broadcasted on a medium, or are you capturing it real time? How is that happening?
Yes, we are capturing in real time. So the diffraction is actually, so you have a detector, right? Back in the day, people used actual X-ray film in a dark room to detect the diffraction spots. Today we have these really advanced. They're about like this big. They're charge coupled devices. They're CCD based detectors. I'm not 100% sure of how they actually function, but they work in a digital manner, and basically the spots that are captured by the detector basically pop up right on your screen as soon as they're received. As soon as the X-rays are received, it pops up on your detectors. You can actually, yes, you can see in real time the X-rays being captured, which is really cool. Sorry?
I'm sorry. Well, are you also rotating the crystal around to get different perspectives? Okay.
Yes, yeah, I was going to say that. Yeah, when you, of course, to solve the structure, you need to capture several diffraction patterns as you rotate the crystal. You'll see the diffraction patterns change as it collects the different the different images. So that's actually a really cool thing you get to see at on the beam line.
So do you have like a library of patterns?
Reference library.
Like a reference library that you can compare your results to kind of make some conclusions?
So great question. It turns out that it's really hard to look at. So there are, to answer your question, yes, so there's the protein data bank, which has all the solved structure, so you'll see the actual protein structure there. And then you'll also see a file with the raw data where you can kind of see, if not the patterns, you can see what's called an index of the patterns, which is an index of all the spots, where they are and how intense they are, which you can work down to the patterns, of course. It turns out with the software that we have, of course, you already have an idea of what is in your crystal. When you take those spots in your diffraction pattern, you actually yes. One thing you do is you go out to the PDB. You take possibly something that you may know and see the structure of, and see if the data there is similar to or matches the diffraction you have now. Unfortunately, that's not useful for if you have a protein that's never been crystallized before, right? Unfortunately, that's a problem, and that's something that's called the phase problem, because your data has to be, of course, in phase to be able to solve the structure. So there's a lot of techniques that we try to use to phase brand new structures. I actually luckily haven't had to do any experimental phasing like that, but there's grad students here who have done it. And one way to do it, people do is things like heavy atom soaking, which you can take your crystal, soak it in heavy metals like gold and things like that, and the gold will help you. When you find the location of the gold in the diffraction spots, you're able to work back to solve your protein structure in that way. But yes, typically I would say 90% of the time, yes, you can go to the protein data bank and use models there to help you with the structure, with the diffraction that you have in front of you.
I just want to say a question. You guys have another question? I have a question. I wonder, is it possible that you can turn your camera and show us a few things that's really cool in this lab?
Yeah, absolutely. So let me see if I can. I'll have to make sure I can I'm showing you guys the right thing. I'm going to full screen this camera view so that it's visible. But okay, right here is our microscope we use to visualize our protein. And right here we have a lot of. Actually, this will be great. This will be great to show how we actually take the crystals out of the solution. Of course, these trays are what contain our protein crystals. The way we to scoop them out of solution to put on the beamline is through this thing called the crystal wand, and we use those are crystal loops. So I'll take one out for you guys. Okay. So this is it's what we call a loop. And the very end of it is like a little loop. So it looks like I wish I had like a magnified image of it, but it's almost like a little circle. And the circle is like a net that we use to net our crystals out of the solution. And then you take this loop, and then you actually mount it right on the beamline. You actually have special tweezers, tongs that we can use to take them and put them right on the line for X-ray diffraction. So This is like the manual method of doing it, but nowadays, a lot of times, a lot of beamlines have robots that are able to just take them right out and do them in a much more controlled way. And that way you don't have to go back into the beamline. You can just stay right out and let the robot do all the work for you there. That's nice. Other things that we have here are, let's see, we have a we of course, these are crystals. They have to be cool. So we have a liquid nitrogen. You can see to give you a sense of how many crystallization files we have ongoing. All these players represent here and on this side. So we have everyone in our lab has a position like a shelf all to ourselves. So yeah, this is basically our setup here for crystallization. We also have another facility, about a 15-minute walk across campus that we sometimes go to set up initial crystallization trays. It's another robot that sometimes if we're try a lot of different trays, because maybe something's a little tricky to crystallize, we use that. It's called the Mosquito.
Thank you very much for your time.
Yeah, absolutely. I hope you guys were able to hopefully understand my babbling. So I know I was I apologize in that way, but it's very easy to kind of get me going on my research. So that's sort of how it works there.
We're excited for research right now. We definitely learned a lot from you. Thank you.
Great. All right. Thanks. You guys have a great day.
You too. Bye.
Bye.
All right, so we're a little bit over, so you guys have to rush off to other classes, other things. Thanks for showing up.